Let's go. Okay. Good morning, good afternoon, everyone, wherever you are. We're excited to have you back for our ninth installment of Get a Grip. This is the Parcel Induction Saga Part 2. So earlier this month, Alex walked you through our origin story and how we got started, the milestones along the way, and how focusing on standardizing success helped us become the go-to name in parcel induction across North America and Europe. Today, he's going to pick up where he left off, but this time it's all about optimization. So you've got a robot cell that works. Now what? What should you be thinking about and how to take it to the next level? So my name is Lisa O'Brien. I'm your host today. And a couple quick notes before we get started. As you've already, if this is your first time here, as you can tell that this is a conversational webinar. So we encourage you to flip on your cameras if you want to, just because we want to get to know everybody. But also, if you have a question, you can raise your hand during the webinar and we'll call on you to ask it. Also, if I just can't get to you during that time, put your question in the chat. We can come to it afterwards too. That's fine. And then lastly, this is being recorded, so we'll follow up with an email either by the end of the week, maybe Monday, and send a link to the recording as well. So before we dive in, I'm going to welcome Alex Berry. He's our presenter today, and I'm going to hand it over to you, Alex.
Awesome. Thanks, Lisa. Yes, welcome to the webinar, guys. And like Lisa said, this will be a continuation of the webinar earlier this month, which was, oops, too far forwards. Never mind. We'll let it go with the slide. So earlier this month, I covered kind of from like 2011 to 2022, where the thoughts were
Really
made with
quick.
this.
Alex, can you share your screen, please?
Oh, I'm not sharing yet. Thank you.
Yeah.
Super sorry, guys. Thanks for catching that. Now y'all know I gotta have Lisa here. So let me make sure this is back on controls mode. Yes, next. So again, covered, about a decade or so of, kind of the first pass at software and using robots to kind of make decisions using computer vision and AI, and then getting into, the parcel induction application, and, successes, failures, and things that, are foundational to plus one robotics, and then things that shaped our applications moving forward. And I really like this video of me playing pickleball terribly, but I did add the note down there, guys. I'm a golfer, not a pickleballer, so, you know, don't expect to see anything good when that paddle's in my hand. So we'll jump right in on part two. So this is essentially picking up at around the 2022 mark as far as time and our step into the Induct One product, right? The dual arm solution that is, we'll call it. You say I want to Induct One, you give us a check, you get this machine, and I want to focus on a little more of the why it does what it does, why it's designed the way it's designed, and the impact that has on, end users, customers, and the application just in general. So we'll go over what I think is the most important point I touched on a little bit in last webinar, which is the gripper, or we say like eye-hand coordination, but the vision can't go pick the item up and put it somewhere, right? So you need to be able to grab it, right? And I want to talk specifically about the ICC gripper, and speak to that point. We talk about exceptions, and we use that term a lot, but they exist because there are rules. There's rules, which is the happy path. You picked up a package and you put it where it's supposed to be. That's good. If you didn't do that, there's an exception. I'm going to talk about a lot in optimization, and not in the obvious ways in which things are unoptimal, but in the ways when you're trying to take something from 99.5% to 99.6%, and what does it take to really do that. Then I'll get into some mathematics of why one arm is not half of two arms, why that's not a correct statement, and then we'll kind of do a big sum up at the end. So first, the gripper, and I like the phrase one cup, 2 cup red cups, but it's not blue cups, it's black cups. So it didn't quite work out on my rhyme, but the reason the gripper is important, especially in parcel induction applications, and specifically with Induct One, which is designed for very high speed applications, high utility applications, where you're going to need really high throughputs, many hours of the day. We have many systems out there that are not the Induct One, that are just a single arm, and they do 1200, 1400, 1600 per hour, maybe the lower utilized as far as hours a day. But this specific product is developed for that need. I need more than 2000 an hour. I'm going to be running this thing 12, 14 hours a day, even, or longer, and I need it to be always at that level. So how do we build that robustness and that capability into it? I've obviously put in here the first note to poke fun kind of at us that it did take 1 billion picks to kind of start to figure out like we need a better gripper that can do the things that we see need to be done at the machine level to make it very useful machine for people. And I'd say that because it's very obvious, like it's the Monday morning quarterback, and it's very obvious when I tell you all the things, like, oh yeah, well that makes sense, right? Well, of course you'd want to do that, but it takes a long time to figure out what it is that really makes sense on how to do it. So the first one is just that generally speaking, you cannot present packages to a robot one at a time, right? And if you could do that, the front end controls for that or the processes that would need to be there are expensive or impossible. And generally, the piles that you're going to get, the gripper is bigger than the area in which it can pick. So that's part of zoning control, say. Like to make sure that only the amount of vacuum, the area of vacuum that's needed, it can be put down there. I touched on it last webinar as well that we had the compensation in all the springs so that they could conform to the packages, especially with poly bags and having softballs in there. But even the lightest spring that you could put in there, it's still strong enough, and even this the compression of the suction cup is strong enough to like hold lightweight items with it, even without vacuum, right? Just press with other stuff. So that wasn't going to work either, which is why these cups stay out of the way and they only extend as needed, right? So that then you don't get the tag alongs, you don't get the clips. So those are kind of two just foundational technology improvements or achievements of this gripper. And when we set out on, what we were going to do, and we were going to start from scratch and design our own gripper, just all right, we know all these problems that we have. We have enough systems that deal with these issues, and how do we take these systems that are, let's say, 95% to 97.5%? How do we get 2.5% more, first pass yield out of it, let's say? Which is that you went to pick, you picked, and you placed, and you placed, and it was one item, and it was not too big, and it could be, moved out of the machine. So the goals were pick it every time, pick it the first time every time, and only ever pick one item. So those functionalities were what brought us into we need to be able to extend cups. We need to be able to only put cups out that can fit in the area, right? And there was a lot of testing that went in to figure out how many cups, how many layout, the disparity or the distance between center points on cups, things of that nature to come up with this design. And some of it may be a little hard to grasp, so I put some impact down in there for people that want to see like a real number with it, which is those are fair numbers, right? If you pick up two items, you place it and you have to recover it, you're taking about a 3 picks per hour hit, right? And you may say, well, that's not that much. Well, I mean, if you only did it once, sure. But, if you have the capability of doing that on somewhat frequent basis because you don't have capability in the gripper, I mean, you could be talking about, 100 picks per hour, some very significant amount of throughput loss because of all the times you have to go back and fix your problems. And then the last one is even harder to kind of get your head around. But if we go to pick and we don't come back with an item, we miss it, that's at least a 1 pick per hour penalty because we went through a motion of picking and we didn't pick anything. So again, if you only did that once, it's only not a big deal. But if you have the capability of doing that, or if that's one of the weak spots of the gripper, you're probably going to do it a lot more than once, and you're going to end up with those throughput penalties. And especially in the parcel induction world, throughput is the driver. That is the key. People do this job very fast, and there are millions of packages, in some cases, millions of packages per hour that need to go through facilities. And if you guys been on other webinars, you've probably seen me run some videos of this tool before that we use to do regression testing and other types of software testing in-house. But I'll just point out here, it goes obviously very fast, but wherever you see red, that means the cup is retracted. And whenever you see green, that means the cups are extended and are to engage the item. You'll see even in most cases here that all these cups on this configuration are extended. And this is just flat mail and boxes. There's no poly bags in this mix. This is a very easy mix to go through. And I specifically wanted to run this test because even with just boxes and flat mail, like there's nothing complicated here. You'll still see plenty of times where 1 cup's off or 3 cups are off or a certain side's off and a certain side's on. So even in the simplest of applications, we found utility that this still improves the first pass yield. And the first pass yield is the biggest driver of our throughput. So we did find the improvements of which I was talking about earlier. So next I want to jump into exceptions. And that's kind of how I describe them to people. Things that are too big, too small, wiggly, you drop them. Anything that's not I went to pick one item and I placed one item and it was, in spec and a good placement, and thus it can be put onto a sorter. So those are the rules. As I say, this is the rules in which the robot has to follow. I do a lot of personifying of my robots when I talk about them, but this is the rule, right? You pick an item, you place it. So you can see in my title up there. Maybe you guys don't like alliteration. I do, but if we pick two items and say we don't recognize it and they leave the machine and it gets a barcode scan of one barcode, those two items are not known, right? It's not known that I picked up those two items and now I'm going to ship uh, to Joe's house the jelly beans that Jill ordered. And Jill's going to be sad because she didn't get her jelly beans. And Joe's going to be like, great, I got free jelly beans. Awesome. What a good day for me. But that's still the wrong thing, right? That's the wrong thing to do. That's bad quality. And that third bullet point down there comes from my manufacturing days in Corvette Composites, which is if I made 1,000, fender liners and every 1,000 is out of spec, did I make any fender liners? Was I productive at all? Like, did I do anything useful? Like, no, you didn't. You just wasted a bunch of time and materials. Um, and I'll start with that top point before I get into this flow path. With the green path is happy path, right? Things come to robot picks in places, and then they leave. But you need to what I said about depalletization, right? Which was the number one thing you can't do in depal is have the robot knock the pallet over. Like you can't have the robot do something because what the vision system says or the system that knocks the pallet over. People are going to hate your robot, right? Because it's doing a lot of work. On induction, it's don't do something that stops the sorter. The sorters take a little while to spin up. They can generally be difficult to kind of get access to repair an issue that you may have done. Say putting too big of a item on there and causing it to get blocked, and someone has to climb up there and get it out. So number one rule is don't stop the sorter. The number two rule goes to my point of the green button, everybody gets to leave, red button, everybody gets to go home, and they don't have to interface with the robot very often or at all, which is the robots need to be able to handle their own problems. One of the problems is that robots have an item that comes in, maybe it's damaged or whatever reason, but it can't pick it up. It just can't get a grasp on it. Well, what do you do if there's nowhere to go? If the only way out was to the sorter, but I can't pick it up and put it to the sorter. That's what those red lines are for. The pass-through rejection handling. Obviously utilized well for oversized items that come in or, trash that needs to just get out of the system, ripped up labels and, a lot of, stretch wrap, things that just come through there that we just need to get rid of. They're not for picking, but also in other situations where you just are in a situation that would generally require somebody to come in and fix it. But let's say you've only rejected, three packages in the last 15 hours. Like, well, just reject this fourth package and then get back to work. So this is part of how this system itself and other systems that, we designed and our partners have designed, this is how these systems maintain that I'm going to do productive work and you don't need to come over and help me out. And pass-through rejection is very important. And then unrecoverable stuff on the place side. And I'm going to show you guys a video of that right now. This is one of our torture tests where we put all kinds of weird stuff in here on purpose. But those two packages are taped together to signify a conjoined package, right? Well, it does happen in the polybag world quite frequently, or I mean, not quite frequently, but probably close to 0.5% of the time, frequently enough. But you need to have something in there from a control side, from vision side, from whatever the aspects you can manage to deal with But if you can't, like conjoin packages, there's nothing the robots can do to take those packages apart. Like in people in the real world, they just rip them apart, right, and then throw them on the sorter. I mean, that's kind of hard for the robots to work together and rip the package and not risk damaging everything under the sun. You see, he picks, he places, and the white box on the end is just to block it from being able to reject it off the pick side. Picks places like I got two items. Oh, go fix it. I got nothing again. Like this is really weird. All right, let me get it right this time. It's like, nope, you still got it wrong, man. We don't know what's going on in this situation. Don't call some. Just reject those packages and get back to work. And then you see it just gets back into autonomous operation. This is really important in the aspect. Obviously, it doesn't help your first pass yield so much, but it's really important in the aspect that these robots remain productive. They don't require people to come intervene with them. Just as a whole system, they are a useful tool for an operations team. And these torture tests are hilarious to watch if y'all are ever at headquarters and we're doing it on the QA side and Jose's wrecking it. It's really fun to watch the robot figure out how to get out all these problems. which this one leads right into what I was saying about milliseconds add up. Milliseconds are tiny, tiny amounts of time. We'll talk about this one phrase, micro starvation in particular, but anything that's going to stop the robot from picking and placing, we're going to categorize as dwell time. And I've taken Harvey McKay. If you guys aren't familiar with him, he wrote some books long time ago, but solid books. And one of his, I don't think he intended this phrase to mean it, but I read this book, years ago now. But don't water your weeds. And the way I took it from a process engineer was do not accept that you have to have bad parts. You have to just deal with the the negative aspects of it. Part of this is the lean manufacturing mindset as well. But don't water them was essentially me saying don't just let them exist in your system. And for robotic applications specifically, I think about machines in general, but I think about dwell time, right? At what time is the robot not moving to go pick up something or place something? Right? If it's not doing that, then we need to limit that as much as possible. And I put a little math in here, mostly to show how a tiny amount of milliseconds, a tenth of a second, only 100 milliseconds, what that really means. So let's say we have, induct one, and let's say its stable machine rate is only 2,500. It's a little faster than that, but let's say easy math, and we have a 100 millisecond delay between a pick and a place every time. It's just the nature of the controls architecture or whatever, right? There's just something that makes it have to wait 100 milliseconds between every pick and place. If you did that, right, if just that little amount of time every time, that is almost 200 items you did not pick every hour, right? Every single hour. These are huge throughput killers, but they're not easy to see, like visually just watching them, right? They're not easy to understand what the root cause of the problem is in just running the system for 5 hours. Right? It took us a long time, many, many years, which is what I talked about earlier this month. It took us many, many years to start to figure out where these slight dwells were and slightly unoptimized situations were, and then find remedies to them or re-architect things. I don't know how many times we've rehashed architecture over the last like 8 years on how do we avoid this happening, right? How do we make sure we're not wasting time waiting? Right? And wasting time for the conveyor to stop moving so we can get it. Wasting time on bringing packages in because we should have brought them in earlier. Those types of wastes can be very significant to your average throughput, especially over time, right? I mean, you think about something like this going on for months and months and months. I mean, you're losing days worth of productivity that you could have had if you didn't have that dwell time. So, and a few years ago, we did coin this term in-house. Maybe we didn't, but it's the first time I ever heard it. Micro starvation, which was essentially anything that was causing dwell time less than 200 milliseconds. And we began to optimize around that. And a lot of that optimization became the standard, which then became part of Induct One and how it was architected. Um, I'll put it out there because trying to be honest, Induct One is not a 0% dwell time. There are still dwell times in there. We still tweak on them. Some of them are unavoidable in the sense of what we want the system to be able to do, how we want it to be able to handle the work coming in, and how we want it to interact with the existing infrastructure around it. So some of that is like, okay, well, if we want this to happen, this is a requirement to wait and check on that first. So it is what it is there, but we've really optimized that around a lot of different scenarios that are very commonplace in the bulk and feed to sorter application. So we won't go into all those now because I don't have time for it, but there's some cool ones for sure. And the last point on it is the physical structure of that, even things down to like the pedestal that the robot's mounted to on there. It wasn't a situation where we're like, oh, we need a pedestal for this robot. What do we got? It's like, oh, I got this one over here. It's like 312 millimeters. It's like, okay, we'll just stick that pedestal up there and we'll go with that. A lot of simulation, a lot of time was spent on optimizing the physical layout, the robot, and the pick and place location, the belt width, the belt length, the belt speeds, the controls engineering between the robot, the belts, the vision system, the safety systems on and the HMI on. How do we make sure that none of these are the PLC's not waiting for the robot to do something when the robot could have already told the PLC that, those types of situations. And now I'm going to get into math that doesn't work out, but it does. but it doesn't work out, right? You would say one is half of two, but one arm is actually not half of two arms. And part of having a dual arm system, and one of the things we had found out, especially in like that video I showed of the customer with those robots in series, is that if they're independent of each other, say independent enough of each other, they become a redundancy, right? In the sense of one failure doesn't mean the whole thing is dead. And that's everybody's friend because we don't want things to break, but we also assume that these robots are going to be in here for years and years and years, and sometimes things will break. Well, if you can turn one robot off, and the other robot can work, like you at least get something. And what we found is that you don't get half. So if we say it was 2,500, you don't get 1,250. You actually get like 1,480. And it's like, well, why is that? Like, well, we didn't quite expect it to be such a bigger gain. We've seen it as high as even like 65, 70% of the throughput with one arm. So we started looking at all of our block time and stuff, which is why I have that cool robot saying sorry to the other robot. Which, is my sense of humor in there for sure. But right, the robot did a double pick. It's I gotta go fix it. So robot one now is blocked, right, by robot two. Do we like that? It's not great, right? Not great to double pick. It's not great to block the other robot that's carrying on with its life because it hurts your throughput. But quality is very important, right? If we send two out, we don't get to count it. But it's also really important to the people on site that have to work besides these machines, right? Handling these, being polite, I always call it the robots being polite with each other, um, is very important in avoiding situations in which human intervention is needed. For example, one of the situations that can occur if you don't have a good handshaking and a good architecture between two robots working kind of in the same area is that one robot kind of gets ahead and the other one had some problem and then another one never gets to work for 45, 50 seconds. Again, I showed some of that in the other video in the webinar earlier this month, and you can go back and check that out. But that was a big focus point on when we are going to have to, wait on each other, let's make sure there's a really good reason for it. Like, don't shoot out two items just because the other robot's ready and he has to wait. And then I put in some other weird failures that could happen that could make one robot go down. Um, which again, we try to design against that and stuff, but it's inevitable that something will break at some point. And if it was a one robot arm system on this cell, then it would just be a non-functioning lane unless you're going to stick somebody in there and have them work around it. But this is not the case with Induct One. So there's some, convenience in there of having that redundancy for sure. And I'll be finishing up with this one with no words, just a video, which is to kind of wrap up this whole point of that this machine is designed to do a certain job. Again, we have a lot of machines out there that are just single arm systems. They're lower throughput, lower utilized, lower cost, maybe their systems to solve other needs for certain applications, certain customers. But this one is specific to do this job. And so what is the job? This is the job, right? This is not my test package set if it's not obvious. But they're going to come in. We're going to have times, hours, days maybe, but we got nice, easy stuff like that. Everything's spread out pretty nice, just kind of a bunch of big old boxes that are almost as big or bigger than the gripper, make them a little easier to go pick up. It is a pretty straightforward day. This thing's just going to hum along here. If you give it to this thing for 20 hours a day, it's just going to do, 25, 2,800 parts an hour all day. Just keep on running. And then also, the very next scalar that dumps could just be, or maybe the next 20 galers that dump could just be nothing but a big giant pile of all white poly bags, which if you're not familiar with computer vision difficulties and struggles, if you're looking at that pile with your own eyes, then you recognize that. How is that? How do I tell what's one item and what's not one item and what's two items? And some of them are really full and some of them are really empty and some of them swing around a ton. Um, this is the job to be done. I need to handle this for the 5 minutes that I have this, and the next 5 minutes is all white, and the next 5 minutes is back to boxes, and the next 2 hours after that is nothing but black packages or paper mailer, bags. But this machine is optimized around this job to be done. And it's a highly variable job that is extremely demanding on uptime and throughput. And this is where we got to. And it was short and sweet one today. Any questions? All right, looks like we're good. Y'all think of
Questions
questions
though.
in a minute. Y'all can jump in.
All right. Thanks, Alex. So, got a couple announcements for you guys. This is where we're going next, so actually today and tomorrow, our president, Avi Barkay, is in Boston for the Robotics Summit and Expo. So if you're there, make sure and send him a message on LinkedIn, maybe stop by and say hello. And he's speaking today too. So, and then next week is the MHI spring meeting in Houston. We've got a team headed out there as well. And then of course Automate's coming up in Michigan next month. So Automate next up. Alex, next slide, please. We are going to be having a happy hour with our friends at Yaskawa. And so if you're headed to Automate, we'd love to see you. You can go ahead and register with this QR code. It's just a short walk away from the Huntington place at a location called the Waterview Loft. So anyway, there'll be the robot pub that Yaskawa likes to bring at all their events. We've got a DJ coming out. We'll have ping pong. It'll be a good time, guys. So please mark your calendars and register. We'd love to have you. And is there a question in the chat? Okay. All right, awesome. Thanks for the comment. I appreciate it. And that's it for us today. We'll be sending out the recording. We'll also send out information in a week or two on the next webinar for May. So that should be May 28th, I believe. But we've got some details to firm up on that, and then we'll be sure and share the information. But that's all we have for you today. If you have any questions, please follow up, connect with us on LinkedIn if you haven't already, and enjoy the rest of your day. Thanks so much, everyone. Bye.
All right, thanks.
Yeah, guys, have a great day.